So like I said yesterday, I'm going to now walk through the statistics of a factorial ANOVA. Not the computation of them, but just kind of mathematically what we're basically doing. So I'm going to start with a simplest example. This is a 2 by 2 example. You can see that factor A is the dosage level of a drug. So you have two conditions or two levels of the independent variable, low dose and high dose. And the second independent variable, or the second factor, is gender, which has two levels, males and females. Now, within these four cells, we might have many different participants. For instance, here in the condition where we're considering those males who are taking a low dose, we might have 10 participants, 10 subjects, and we might have scores for each of those participants on some dependent variable. Let's say that this is happiness. I don't care what it is, but let's say that these are levels of happiness on a particular low dose of a drug. You could look at person number 1 here has a 3, person number 2 has a 3.7, and so on. And you could take the average of these 10 people, these 10 males who are on the low dose, and you would see that cell A1B1 has a cell mean of 3.05, that's the average of all 10 of those, and a standard deviation of 0.927. We could do the same thing for the males taking a high dose. These participants numbered 11 through 20 have scores that are a little bit higher, so they're perhaps ranging like a bit more happy on the high dose. You can see the cell mean here is 5.58, which is a bit higher than the 3.05. And we could do the same thing for the females down here. We could have participants 21 through 30 and 31 through 40, and each of those could have some scores. So you have a cell mean of 1.7 and a cell mean of 8.25. So if you just kind of take an overall look at these four conditions, you kind of start to get a sense for what might be going on. Males have lower happiness levels when they take a low dose and higher when they take a high dose. Females also have lower when they take a low dose and higher when they take a high dose, but it looks like their extremes are much larger. There's a much bigger gap here between 1.7 and 8.25. Now, I mentioned yesterday, or in the previous lecture, that we call differences between different levels of an independent variable a main effect. If we run a statistic and we find that there are, in fact, differences, we call that a main effect. So we could say that if we're going to compare, for instance, the males versus the females, ignoring their dosage, we would average over here all the males, regardless of the dosage they're taking, and we would see that the males have an average of 4.3. And the females, ignoring their dosage, just averaging across all 20 of these people, regardless of their dosage, they have an average of 4.9. Now, if we ran statistics on this, we might find, perhaps, that 4.98 was statistically different from 4.3, but I doubt it. Those are pretty similar to each other, so there probably is not a main effect of gender. If we look at dosage and ignore whether people are males or females, and just look at the people who do the low dose, then they have 2.38 happiness levels, and the people who take the high dose have 6.9. Those are much further apart, and I would strongly suspect that if we were to run a statistic, we would find that there's a main effect of dose, that there's a significant difference here between the mean of low dose and the mean of high dose. Now, a main effect, like I said, is the effect of a single treatment factor or variable. It compares the levels of that variable. So, in other words, this would be, like I just said, men versus women, ignoring or collapsing across dosage. So that would be to look at the averages for the males and females against each other, ignoring dose. In statistics, we sometimes call this collapsing across. If we have low-dose patients versus high-dose patients, and we ignore gender, then that would be another main effect, or another test for a main effect. So, for instance, the low dose here has an average of 2.38, regardless of their gender, and high dose 6.92. If we found a significant difference there, it would be considered a main effect. The difference between males and females here, if it was different, it would be considered a main effect. If we didn't have one, then we would have to say that there is no significant main effect of gender. So when you have more than one variable, the scores for factor A are averaged across factor B. So factor A, remember, was dosage, and we average across factor B. In other words, we just take all 20 people who took the low dose, and we ignore whether they were males or females, and we just compute the average for all 20 of those people. So we would take like the high dose, averaging across the males and females, and the low dose and the high dose, and we do the same thing over here. And then the scores for factor B are averaged across factor A. So we would take the males ignoring or collapsing across or averaging across whether they were taking a low dose or high dose. We wouldn't care. We would take all 20 males, compute their average regardless of what dosage they were taking, and just figure out the mean. Graphically, you could see this represented here. You can see the average low dose is 2.38, the average high dose is 6.92, and for gender, the average for males is 4.32, and the average for females is 4.98. Much smaller a difference there. However, the benefit of doing a factorial design is that you can look at interactions, the interplay or interaction between multiple variables. An interaction means the effect of one factor or one independent variable depends on the level or the value of the other. These are often more interesting than the main effects by themselves are. So in this particular scenario, you remember we saw that the females responded quite differently to the medication than the males just when we looked at the means of the 4 cells. In fact, what we saw was that at the low dose, the females were lower, and at the high dose, they were higher than the males. In other words, they had a larger spread of scores. The males had still the same overall pattern where it was lower, their happiness levels were lower with the low dose and higher with the high dose, but it wasn't quite such a large spread. They didn't improve as much. They didn't start off as bad, and they didn't improve as much when taking the medication. If you find that you have non-parallel lines when you graph them like this, in other words, they cross or they converge or diverge in a graph, then that indicates that there's an interaction occurring. So for instance, you could look here and you could say, do the lines cross? Or if they don't cross, but they would cross if they were carried out further because they're not parallel, then you could kind of say, yeah, there's an interaction here. Now, virtually every time you run statistics, you're going to find that the lines are not perfectly parallel. So, how do you know if there's a real interaction or just like not really an interaction and they're basically parallel? Well, the angle here that we see is important. So the larger the angle, the more likely the interaction is to be statistically significant. So if the lines are pretty much parallel, then we could say there's no significant interaction. Whereas if they're dramatically not parallel, then we would have to say that that there is a significant interaction. And typically we would call this the A by B interaction. So I'm just plugging in these letters as stand-ins. In reality, we would use the name of whatever variables we're looking at. So for this instance, we would call it the sex by dose interaction. Now, I want to take a look at what we're doing when we're computing the math of an ANOVA for just a second. When we do a 2x2 ANOVA, you're actually performing 3 separate ANOVA tests. You're testing the main effect of A, the main effect of B, and the interaction between the two. So in this particular situation, you're assessing an ANOVA for the dosage, an ANOVA for the gender, and an ANOVA for the interaction. And you're asking the question, in that latter case, does the level of dosage cause different effects for males and females? Going back one slide, we can see that yes, in fact it does. The dosage causes a much more dramatic increase for females than it does for males. So the impact of this factor, dosage, depends on the kind of the level that you are in the other factor. So it depends on whether you're a male or a female. Let's take a look at another example. So if you look at this graph over here, you've got people that students that are taking a stats lecture and those who are taking a lecture on sexual behavior. Now, if you happen to get a hangover the night before, you're likely to have much higher levels of self-rated sleepiness during the course of the lecture. It's going to be harder to stay awake and harder to pay attention if you have a hangover than if you don't. Now that's kind of what we see here. The lines are higher here where it says hangover and lower here where it says not, suggesting that people have higher levels of sleepiness when they have a hangover. However, you can also see that people are less sleepy during this orange line, during the sexual behavior lecture, because perhaps it's more interesting. So they have lower levels of sleepiness here in this orange line than they do in this blue line. But you can see that the lines are not parallel in this situation. In other words, a hangover might have more effect on sleepiness during a stats lecture than it would during one about sexual behavior. So your hangover kind of takes your sleepiness level during the stats lecture and skyrockets it. It's way high, way sleepy during stats, but it only increases your sleepiness level during a sexual behavior lecture by a modest amount. So you can see that the impact of a hangover is more dramatic in this graph for those people taking a stats class than those people taking a sexual behavior class. However, this might not be the reality of the situation. You might find that in real life that there was not an interaction here, that these lines were approximately parallel, in which case you would say a hangover might affect everyone the same, regardless of what kind of class they're attending the next day. So if you're in a stats lecture, of course, you're going to be sleepier just on the whole than you are in a sexual behavior lecture because it's a little bit more boring. And when that happens, of course, you see like just the overall blue line is higher than the overall orange line, but you see an equal impact of hangover for both kinds of lectures. So the hangover versus no hangover is 2 points higher, but it's the same for a stats lecture. Again, 2 points higher. So you're going to have 2 points higher levels of sleepiness because of a hangover, regardless of what kind of class you're taking. So this is an example of no interaction, whereas in the previous slide here, this is an example of having an interaction because the impact of one factor depends on the other factor. So the impact of a hangover depends on what kind of class you're taking. Now, in the same example of hangovers here, a mean difference among levels of one factor would be considered a main effect. So we have to test for statistical significance to see if there is a difference in the sleepiness levels of people who do and don't have a hangover, ignoring the lecture type. Another main effect might be if there's a difference in the sleepiness levels of people who are listening to stats versus sexual behavior, regardless of whether they have a hangover. So if I go back here and I just look at this slide for a second, we already know there's not an interaction here because we don't see because we have parallel lines. We don't see any kind of crossover, and if we carried these lines out forever, they would probably never cross over. But when we're looking at the impact of a main effect, what we're asking is, if we ignore, for instance, whether people have a hangover or not, whether they feel sleepy in a stats lecture versus a sexual behavior lecture. And if you take the average of 4 and 2, the middle of that is right here. It's 3. That's the average of sexual behavior sleepiness, regardless of whether they have a hangover. And the average of 10 and 8 is 9, which is right here, right in the middle of the line. That's the average of their stats lecture sleepiness, regardless of whether they have a hangover. So the main effect would be asking the question, is 9 greater than 3? And indeed, in this situation, I'd have to say probably yeah. Now we could also answer the question the other way. We could say, what is the impact of a hangover versus not having the hangover, ignoring the kind of stats lecture? So you'd have to take the average of 4 and 10, right in the middle there is 7, and the average of 2 and 8, right in the middle there is 5. And so you'd have to say, is 5 different from 7? So is 5 no hangover, different from 7 having a hangover? Well, it is 2 points higher, so there probably is a main effect there as well. But again, it will depend on the variability due to error, and you'd have to, like, your statistical package would have to put that in the equation and figure out if this is a larger effect than you'd expect just by chance. So we talked about how a main effect and how interactions would look in a couple of different examples here. But again, I want to remind you that once more, this phrase, ignoring, is often worded as collapsing across. And what we mean by that is averaging across the levels of another variable. We're just kind of ignoring what's going on with that variable, collapsing across that variable, and just looking at the other one. Okay, before we move on with more material, I just want to take a second and do a learning check here. So I'm going to ask this question: what means are compared to evaluate the main effect for factor A? So in this table right here, we've got factors A and B, and each of those factors has means, and I want you to answer A, B, C, or D. What are the means that you have to compare against each other in order to figure out, is there a main effect for factor A? Pause your video, figure out the answer, and push play when you're ready. So the correct answer here is D. The reason why is because factor A is here and here. Those are the two levels of factor A. If we average across B and ignore or collapse across B, and we just look at all of these people and their average is 25, and we look across all of these people regardless of whether they're in B1 or B2, we average across all of them and their mean is 10. We're just comparing 25 versus 10, and if those are different, then we say, ah, there's a main effect. Now I'm going to go through some additional exercises. For each of the following, I want you to determine whether there is a main effect of A, a main effect of B, and an interaction. So for each of these, I'm going to show you a table like this and a graph that shows the same data. So this is A level 1, A level 2, B level 1, B level 2. You can imagine this, to make it more concrete, you can imagine these as other variables. Like for instance, we talked about, gender and dosage. So this could be like males and females. This could be low dose and high dose. But once you recognize that level A1, B1 is this cell right here, you have to say, okay, A1, B1 has a value of 1. Over here, we would graph that as A1, B1 is the dark line right there, and so that person is plotted as a 1. Again, if we go back here, A1, B2, that cell is 1. A1, B2 is the dotted line. That is also at a 1. So both of those dots are plotted at a 1. These other two values here, A2, B1, that's this cell, and A2, B2, that's this cell. Those are both 9s. So you can see A2, B2, that's a 9. A2, B1, that's a 9. Both of them are plotted up there. So you can answer the question whether A has a main effect by looking at the two values right here and here of A. And so if we average across 1 and 1, what's the average of 1 and 1? It's 1. What's the average of 9 and 9? 9. So is there a main effect of A? Is 1 different from 9? Yes, there's a main effect of A. What about B? If we look at the levels of B, ignoring A, what's the average of 1 and 9? Well, in the middle is 5. What's the average of 1 and 9? In the middle, again, is 5. So is 5 different from 5? No. That means, is there a main effect of B? No. Now, for the third part of this question, I want to figure out, is there an interaction? So we look over here to this graph and we see, do the lines cross over or are they parallel? If they're parallel, no interaction. If they cross over, then there's an interaction between these two variables. So, since they're parallel, we can say this doesn't have an interaction, and the answer here is main effect of A, yes. 9 is different from 1. Main effect of B, no. 5 is the same as 5. Is there an interaction between A and B? No, the lines are parallel. I have a bunch of other examples that I want to walk through with you, so for each of these, I'm not going to talk through them. I'm just going to show them to you, and then give you a minute to contemplate the answers, and then when certainly pause your video, think about what you think the answers are, and then test your knowledge by pushing play. So in this situation, is there a main effect of A, is there a main effect of B, and is there an interaction? Here you can see there's not a main effect of A because the two levels of A are averaged at 5 and 5. There is a main effect of B because the average levels are 9 and 1. There is not an interaction because these two lines are parallel with each other. What about here? Main effect of A, main effect of B, interaction. So here you should recognize that 3 and 7 are different, so there's a main effect of A. 7 and 3 are different, so there's a main effect of B. And there's no interaction because these two lines, again, are parallel. What about here? Here there's not a main effect of A or B, and there's no interaction because these are the same as each other, these are the same as each other, and these are parallel with each other. So no matter what condition you're in this study, you always get 5, no matter what, so there's no differences based on the factors. What about this one? Here there's a main effect of A because 3 is different from 7. There's not a main effect of B because those two values are the same. And there is an interaction because these lines cross. What about this one? Hopefully you're getting the hang of this by now. The answer here is yes, yes, and yes. 5 is different from 1, 5 is different from 1, and these lines are not parallel, suggesting there is an interaction between these two. And if we look back at the original data, we can see what's going on. Let's imagine this is gender again. These might be females, and this might be a low dosage here. If the females take a low dose and they have really high scores, but males who take a low dose don't, then we would say that your impact of taking a low dose depends on your gender. If you happen to be a female, this B1 line right here, then you can say, oh, when we take a, oh, I guess I mixed that up, but anyway, you can say that only in this one condition do people get a different value. When they, like say if females take a low dose, then they get really high scores, but if males take a low dose, or if males take a high dose, or females take a high dose, or if males take a low dose, or whatever, then none of those values are any different from each other. They're always one unless you have both of these values together. And so that would suggest that there's an interplay between both of those factors. What about this one? Here you can see that these are the same, and those cross. So you've got no main effect, but you do have an interaction. What about here? Here 5 and 5 is the same, so there's no main effect of A. 7 and 3 are different, so there is a main effect of B. And A and B are not parallel, suggesting that there is an interaction here. What I want you to recognize here is that we just saw every possible combination of main effects and interactions. Sometimes there was a main effect of A, sometimes not. Sometimes there was a main effect of B, sometimes not. Sometimes there was an interaction, sometimes not. But they were all mixed up and random. Like, all of those different conditions did not depend on each other. So this suggests that main effects and interactions are independent of each other. Even if we know there's a main effect of A and a main effect of B, that doesn't mean there will be an interaction. And if there's no main effect of A and no main effect of B, there still could be an interaction. Or there could be neither, or there could be all of them. They're all independent of each other. Another important principle that we need to understand here is that interactions supersede main effects. What I mean by that is, if you have a situation like we talked about yesterday, where the therapeutic alliance matters a great deal, or if in this situation the type of response to therapy depends on gender, then what you're going to find here is that the whole story is what you need to interpret, rather than just like one of the main effects or both of the main effects. So you have to focus on the overall pattern of results when you get an interaction. Here's why. Ignore this graph for a second, and let's just look over here at the main effect of therapy. It shows that before therapy, people were low, and after therapy, people got better. If you look at the main effect of gender, it shows that males are poor and females are better. But is that really what's going on? Is it true to say that males are worse than females? Well, if we look back over here, males and females were the same before therapy. So it's misleading to just say males are worse than females, because at one point in the study they were the same. Is it accurate to say that that therapy was effective, that after therapy people got better than before? Well, not really, because males didn't get better. They were the same after therapy. Females got better, but if we just look at the main effect of therapy and ignore the gender, then this right here is misleading. It suggests that that everybody got better, when in reality, only females got better. So what we're finding here in this graph is that when females were measured before therapy and when males were measured before therapy, everybody was kind of bad. But after therapy, males stayed bad and females got better. So whatever treatment we're trying to give right now is working for females but not for males. That's the story. The overall pattern of results has to be interpreted, because once you have an interaction, it would be disingenuous to talk about the main effect on its own. If you ignored this and just talked about these graphs right here, you would be telling a story that says people got better after therapy, but females are a lot better off than males. And neither of those statements is true, because in reality, only some people got better after therapy, and only after therapy were females better off than males. I have a couple learning checks before we finish our day here. The first one is, if a two-factor analysis of variance produces a statistically significant interaction, then you can conclude which of these things. Pause your video and play when you're ready. The correct answer here is D. The significance of the main effects is not related to the significance of the interaction. Remember when you're doing an ANOVA for a factorial design, you've got multiple independent variables, and you're assessing, is there a main effect of the first one? Is there a main effect of the second one? And is there an interaction? And you have 3 different ANOVAs that are assessing each of those 3 things. And if you find that there's a main effect, that might mean there's an interaction, or there might not be. If you have a main effect of one variable, you might or might not have a main effect of the other variable. In fact, you might have neither main effect and still have an interaction. All 3 of these things are independent of each other. So just because you know one part doesn't mean anything about another. True or false? A disadvantage of combining 2 factors in an experiment is that you cannot determine how either factor would affect participants' scores if it were examined in an experiment by itself. Pause your video and continue when you're ready. The correct answer here is false. In reality, just like we saw a couple slides ago, you can still assess the main effect of one variable and the main effect of the other variable. You can know what would have happened if you had ignored one of the factors. Like in the case of therapy, effectiveness before versus after, and considering gender, you can see that if you had ignored gender, then you would have found that people got better after therapy, but you wouldn't realize that there was a more complicated story going on. That doesn't mean that you can't assess the impact of the therapy ignoring gender. You still can. You can do a main effect. But when you assess that, if you have multiple factors, it's disingenuous to interpret a main effect in the presence of an interaction. So while the answer to this is false, it is a little bit misleading if you just only interpret the main effect without considering the interaction. What about this item? 2 separate single-factor ANOVAs provide exactly the same information that is obtained from a 2-factor analysis of variance. True or false? Pause your video and continue when you're ready. The answer here again is false, and the reason why is because in 2 separate single-factor ANOVAs, all you would learn is what the main effect of the first factor was and the main effect of the second factor. What you get from a two-factor analysis of variance is the interaction between the two variables. So that's a third piece of information that you wouldn't get if you just did two one-way ANOVAs. That's all I have to introduce before the reading. Now that you have kind of a general framework of what factorial ANOVAs mean and a little bit about the vocabulary, you should be able to follow the reading a little bit better.